How do computers think? Well, in this video, I'll aim to answer this question through first principle understanding to give you the premise and the motivation to study the first subject in the journey of computer science, which is digital systems. So, hi everybody, welcome back to my channel. And with this video, we start our first subject in the journey of computer science, which is digital systems. So in this video, I'm going to mainly cover two things. First is that first principle understanding to answer this question, how do computers think? And second is building a mind map of various topics which comes under the umbrella of digital systems. All right, so how do computers think? Well, they don't. What they do, they act as if they are thinking. Behind the scene, what they actually do is calculation. Millions and billions of calculations per second, sometimes trillions of calculations per second. These calculations are of primarily two types: arithmetic and logical. Arithmetic calculation involving all the arithmetic operators we are familiar with, like addition, subtraction, multiplication, division. Logical operators which we might not be that much familiar with, example like and, like or, like not. Altogether, using arithmetic and logical calculations, this is called computation. So a computer without having logical calculation ability would be called a calculator. All right, now with the capability of the logical calculation, computers become capable of processing something called a flowchart. Something that we'll see in the course sometimes. Let's say it's the study of algorithms, or if you're already familiar with flowcharts, you know what they are. But the whole point of having this logical and arithmetic calculations together is to have a capability of processing flowcharts. The next inevitable question from here is, so how does a computer look like? Well, to answer that question, we need to cite a document written in 1945, published in June 30, 1945, by a group of scientists headed by John von Neumann. And this is a document that talks about a prototype design of what is referred to as a very high speed automatic digital computing system. This system was initially started being developed as a miniature or a prototype model of a system which now we call a computer. In this document, we find the earliest example or reference to the architecture of a computer. So, architecture of an engineering system is similar to the anatomy of a living being. It talks about the various organs and how they communicate, how they work together. Similarly, in the architecture, we see different components and how they come together to achieve a given goal. This architecture is now referred to as von Neumann architecture. It has other names as well, like stored program architecture, load store architecture, which simplifies the design of a computer in the following way. So, von Neumann architecture basically comprises of two entities, namely a processor and a memory. Between these two elements, there is a highly available and reliable communication fabric called a bus. The memory is made up as an array of memory cells. Each memory cell is capable of storing some information. The programmer would write a program using a programming language encoding the logic, and this program will be loaded into a segment of the memory called the program block. Now, this program would be written to solve some problem. For example, finding the average of 1 million numbers. So these numbers would be called data, and this data would be stored in another segment called the data block. That's how the memory is organized. There are two blocks of memory, program memory and data memory. Mathematically, you can say the program represents the F and the data represents the X. In the processor, we'll be having three units. The top one will be called a register, which is responsible for keeping temporary information inside the processor. An arithmetic and logic unit responsible for doing all the arithmetic and logic operations, because it's a computer, so it performs calculation which are of arithmetic and uh, logical in nature. Therefore, we have this unit. And we need another unit to do the orchestration between, let's say, the communication between the memory and the other components like ALU and register, called the control unit. The process is as follows, that this program would be a sequence of something called an instruction, and an instruction is an assembly of two components, namely opcode and operands. An opcode is a codified operation that says what to do. For example, if I want to do addition, then add could be an opcode. Operand would be the data on which the operation is applied. So if I want to add 5 and 6, then add is the opcode and 5 and 6 are the operands. These operands are usually kept in the data block and referred in the operand section. When we start the computing process, the opcode comes to the control unit, the operand goes to the register. Then the control unit tells the ALU, based on the opcode given, what arithmetic or logic circuit to turn on or off. Once done, the control unit then tells the register that, hey, I have told the ALU to turn on the respective circuit. Now you can send your data. Register would then send its data to the ALU blindly, and because the only circuit which is needed at the moment is turned on in the ALU instructed by the control unit referred by the opcode, therefore the data only passes through that circuit and the result comes out as the result of the operation. This is what we refer to as an execution cycle, and this is how every single computer in the world operates, especially the classical computer, because quantum computers are now coming into the place, so we will not talking about those computers. Any classical computer, talking about the display board in a railway station to the supercomputers, they all follow this procedure, and this is something which is laid out by von Neumann architecture back in 1945. Now, why is this architecture relevant in our discussion? Because, as I mentioned, this architecture is referred to as the architecture of what was called a very high speed automatic digital computing system. So these components like register, like ALU, like control unit, the memory, they're all considered to be a digital system. Therefore, we study this subject, digital systems, to understand the elementary constituents of a computer. Right. So far we know that how computers think. It doesn't. It does calculation involving arithmetic and logical operations called computation. And this computation is performed by a device called computer, which works as follows. The next question is, as all computers are digital systems, so how can we formally define digital system? So digital system trivially is a system that is responsible for processing digital information. But it doesn't say much. To understand exactly what they say, using our first principle understanding, let's break it down and answer these two questions: what is digital and what is a system? So, digital, the word comes from the word digit. Digit means discrete information. Information means processed data. Data means set of raw facts. Facts are something that you cannot deny. So, what are those facts that we cannot deny? These are physical measurements. Now, in our topics, the various topics we study in this subject, this is the very last thing that we will see and discuss in the study of digital systems. Why? Because we need to understand the use of these measurements first. Then, at the very end, before we finish the subject, we say, okay, so the entire study that we have made is by abstracting all the physical measurements, and we never knew where they come from. Now we know where they come from, and we finish the subject. So, the raw facts based on which this entire subject is built are certain physical measurements, especially measurements which are expressed mathematically in something called a modulo 2 system, which simply means that whatever measurements you get, you divide by 2 and consider the remainder. Now, if you divide any number by 2, the remainder can be either 0 or 1. These are the numbers coming from a number system called binary. So the discrete information that we're actually talking about are binary numbers. So any discrete information we can think of are a series of zeros and one we call bit string. What is a bit? It is a binary digit. So digital means dealing with discrete information. In our case, this discrete information is provided in a binary number system. So in our case, anything digital means anything that deals with a bit. All right, so that's the first part, which is digital. What about system? How do we define system in general? So any system would be a combination of modules which collaboratively work to achieve certain goals. You can think of, let's say, a management system. In a company, various operations they work together. Telecommunication system, railway systems, any systems are combination and collaboration of various modules. These modules that we are referring here, we would be calling them logic gates. Well, the reason they're called gates because they behave like gatekeepers. They control the flow of current in a digital circuit following certain logic derived from a specific algebra called Boolean algebra. So, logic gates are the physical manifestation of the fundamental Boolean operations. What is Boolean algebra? That we'll see in a moment. So, this answers the question, what is a digital system? So, you can think of a digital system is a collaborative combination of various logic gates which takes discrete signals, discrete time signals as input expressed as s of t, and it produces discrete time signal s of t. So if this system represents a function f, then basically what we get is a discrete time signal st getting processed by the function f. This is a view, a mathematical view that we will carry along with us throughout this subject, in the various components of this subject. So, did we answer the question? How do computers think? They don't. They calculate arithmetically and logically. That is called a computation. Computation is done by a computer expressed by an architecture called the von Neumann architecture. Von Neumann architecture describes a digital system that performs computation. A digital system deals with discrete information, which in our case expressed in binary number system. And the system, which is a combination of various components, are called logic gates. So we will see all these logic gates will come together and build various combinations that will eventually perform arithmetic and logical calculations. In combination, we call them computation. And computation is what computers do, and they mimic as if they are thinking. This is the first part of this video, where we understood the motivation behind studying this subject called digital system. The next part is just organizing the subject and the plan of attack, what we will study and what are the reason of studying those components in this subject. So we will mainly start digital system, and we start with the language in which any digital system is expressed. That would be our part 1, and that language is called switching algebra. In various curriculum you might see this as Boolean algebra, but what we really study is an extension of Boolean algebra, called switching algebra. um, the first thing that we will study here is the binary number system. So anyone from the math background, if listening to this video, this would be equivalent to study a field on which this algebra is defined. What it actually means is, if the number system gives us alphabets, then we need a grammar. That grammar will use these alphabets to make meaningful sentences. So that grammar and its rules are called the principles of Boolean algebra. We will also study how we instantiate the Boolean algebraic functions in logic gates, and how these logic gates in combination expresses Boolean functions. Finally, we'll wrap up this part of the subject by minimization of Boolean functions. So the main objective of minimization is sort of optimization. What are you optimizing? Optimizing a Boolean function is optimizing a circuit that represents the Boolean function. Now, if you optimize a circuit, you basically remove the redundant components from the circuits. Means you are reducing the heat dissipation, power consumption, size, and cost. So that's the whole objective behind studying minimization. Now, with these 3 topics, we'll mainly understand how to mathematically express a logic circuit. That will help us in the part 2. In part 2, we'll mainly do the design of logic circuits. Especially, we will study 2 types of logic circuits, namely combinational logic circuits that represents the function of kind y equals to fx, I will not get into details about it at the moment, but it's just for reference. Means you provide X as input and you got Y as output and F being the function. Refer back to this system. So something is missing in this equation is a time. So combinational circuits don't deal with time. What deals with time is called a sequential circuits. So sequential logic circuits can be expressed mathematically as output at present is a function of the input at present and the output from the past. Again, this is something just for reference. If you are not familiar with this symbolism, we will cover them when we'll get to the respective chapters. Inside the combinational logic, we'll mainly study two types of logic circuits. One is the arithmetic logic circuit, which will be helpful to build the ALU, and the control circuit, which will be helpful to build the control unit. So another reason of studying sequential circuit is to get the notion of building a circuit which behaves like a memory cell. We will see the trick to trap voltage, current, or charge inside a circuit to retain information. And that, so the elementary circuit that will behave like a memory cell would be called a flip-flop. And using the flip-flop, we will create two other circuits, namely register, one you have seen in the CPU already, and counter, something that helps a computer to keep counting. We will see counters in mainly inside the ALU and in the control unit. The final part before we finish is the section that talks about these physical measurements, where all these ones and zero come from, how these logic gates are physically realized. So this is where we see how these logic gates, which are the foundation for this subject, digital system, is actually a combination of various kind of transistors. And transistors are electronic devices based on semiconductors. So what are the properties of semiconductors and various kind of transistors that we can exploit to build various type of logic circuits? For example, some could be high speed but costly, some could be slow but cheap. How do we make that balance? That is something we will cover in this last chapter called logic family. And that would be all for digital systems. We understood, for example, what is this subject all about, how do we formally define digital and systems, and the various topics that we are going to cover in the upcoming videos. So I hope this was informative for you. Thank you very much if you are listening up to this point, and please share your feedback in the comments. I would love to hear your feedback, so stay tuned. And until the next videos, this is Saptarshi Ghosh signing off. Thank you.